Hello, Trig and Intro to Calculus slash BC Part 1. So in this screencast, we are going to continue our story. And I always just love the idea of math being a story. Really, as you approach calculus and as you go into calculus, math is just a story. And in this story here, we're going to further our kind of vocabulary bank in talking about functions with special properties. And as I was thinking about this screencast and kind of thinking about how to plan it out, I first kind of made note of the fact that there are so many adjectives that we have used to talk about functions and their characteristics. And some of these adjectives are here in red. You know, we've talked about invertible functions. We've talked about periodic functions, continuous functions, discontinuous functions, polynomial functions. And what's interesting is, talking about functions, why do we care so much about functions, and in particular functions of x, okay? And functions of x are specific relationships between y and x such that if we graphed y equals the function of x, the curve would pass the vertical line test, okay? And more significantly, a function of x has the property that for any x value, for any domain value, for any input value, there is at most one corresponding y or range value, right? And if you really think about it, this idea of a function has been with us for many, many years. For you, I mean, when I say us, I mean you. I mean, you've been studying math through the lens of a function almost exclusively. So, why so much conversation about functions? Why do we focus so much on these curves? And to answer that question now, really, if I were to kind of distill calculus into one sentence, I would say that calculus is kind of the pinnacle in terms of having the fullest vocabulary in being able to talk about functions, okay? So really, calculus, when you think about calculus, calculus gives us the language in its entirety that allows us to fully describe, talk about, manipulate functions, okay, in context and out of context, okay? So that is why all this time, years, build up emphasis on functions has been spent by you. But in this screencast, I'm going to talk about two more adjectives, okay? Functions that are even and functions that are odd, okay? Even and odd functions. And you may have touched upon this in Math 2 last year, maybe briefly, and I'm going to do it very thoroughly here, okay? So the first question is, what makes a function even? Okay, what makes a function even? Well, let me tell you what makes a function even from a graphical perspective. A function is even if it is reflection symmetric over the y-axis. Okay, that's the graphical definition of a function. If it's reflection symmetric over the y-axis. So I'm going to do here, just sketch two examples of even functions. Let's see. Two even functions. And maybe I'll look at this one. I kind of like this little key lime color. It's very neat. Okay, so here's an even function. This is maybe the parabola shifted down 2 units, perhaps. And, oh, I know an even function we've seen recently. What curve is this, boys and girls? Yes, it is y equals cosine of x, right? So y equals cos x is an even function. Oh my, oh goodness, that looks a little bit horrific. Let's just make that a little nicer, okay? So when I say that a function is reflection symmetric over the y-axis, what that means is if you treat the y-axis kind of as a mirror, or if you want to pick up your paper and fold your paper on the y-axis, the function should map onto itself. It should fall onto itself, okay? So that is the graphical feature of an even function. Naturally, if I were to ask you, are all functions even? I hope it's obvious that no, certainly not all functions are reflection symmetric over the y-axis. Okay, what about the algebraic definition of what makes a function even? Well, algebraically, an even function has the property that, that f of x equals f of negative x. Now, we're going to write this down, but I want you to make sure you really understand what this is saying. This is saying that the y value when I input an x value will be the same as the y value when I plug in the opposite of that x value. So, for example, let's just say if that first graph, that parabola, let's say it's f of x equals, let's say maybe get 3x squared minus 4, okay? It's the parent parabola, vertical scale of 3, shifted down 4. Okay, let's say that's this graph over here. Let's show algebraically that f of x is even. So what we're going to do here is let's show that f of x equals f of negative x, okay? And let's see, okay, well, if f of x equals 3x squared minus 4, let's see, so that means f of x equals 3x squared minus 4, doi, and f of negative x, let's see, let's input negative x into x, okay? This becomes 3 times negative x squared minus 4. But negative x squared just becomes positive x squared. So this becomes 3x squared minus 4. And notice that since f of x and f of negative x are equal, they are equal, so that means f of x is an even function. Let's do the same thing for f of x equals sine x, since we have that as our example. Okay, so second example, let's say if f of x equals sine x, which is the graph above, let's show that the algebraic property that f of x equals f of negative x holds true. All right, let's see. And you know what? I'm being very particular, as I always am. Let's just kind of make sure we really box the question so that when you study, or look at your notes in a day or a month or a year, or when you sell these notes on the black market next year, because let me tell you, I've had students do that. Boy, these notes are really valuable. If you make your notes really readable, boy, will they help you not only this year, but next year too in BC Calc, and really, frankly, even in the course afterwards if you take linear algebra or multivariable calculus. All right, let's show this. Let's see. Well, okay, I know f of x equals sine x. I mean, that's obvious, right? But oh no, let's see, f of negative x, that's going to equal sine of negative x. Let's think about this. We talked about this. Remember what I said about how this class we're going to be constantly cycling back, going back and forth between new content, old content, new content, recent content, late recent content. We're always cycling back and forth because it's really the entirety of the story that matters to us. Does the sine of the opposite of an angle have any relationship to the sine of an angle? In other words, if I had sine of 90 degrees, how does that compare with, oh my gosh, Yam, really? I put the wrong function in here. I just caught myself because, good grief, this wouldn't work. So hold on. This Yam, fx equals cos x. My bad, f equals cos of negative x. Okay, that's the graph above. Silly me, this is the graph of cosine x. Come on. Let's show, okay, so is there something that we know about the cosine of the opposite of an angle versus the cosine of an angle? So in other words, if I said, cosine of 45 degrees versus cosine of negative 45 degrees, and how about cosine of 130 degrees versus cosine of negative 130 degrees. Maybe you'll remember your identities sheet. And I remember it was Arusha who did a really nice graphical proof of why this always has to be the case. But you may recall that f of negative x, or cosine of negative x, always equals cos x. So since f of x equals f of negative x, we know that f of x equals cosine x is an even function. Okay? Very good. Very nice. Which then leads naturally into what makes a function odd. Okay? What makes a function odd? So here's the question. What makes a function an odd function? Well, let's do the graphical definition first. If a function is odd, that means that graphically your function is not reflection symmetric, it's called rotationally symmetric. Okay? Then it is rotationally symmetric. And when something is rotationally symmetric, you are not rotationally symmetric over an axis. You're rotationally symmetric over a point, or about a point. F of x is rotationally symmetric about, and that point of rotational symmetry must be the origin 0, 0. Okay, it can't be any other point for the function to be odd. And what does it mean to be rotationally symmetric? This you may have explored in Math 2 last year. When you have a graph that is rotationally symmetric about a point, what that means is if you were to take that graph and spin it 180 degrees about that point 0, 0, the function should land on itself. So let me give you an example. Probably the most famous example is this one. Let's do this one. I'll do 3. How about that? Okay. Let's do, this is kind of it's like the graph of y equals x cubed. Okay. This is f of x equals x cubed. Let's do this one as well. I'm going to give you 3 graphs. How about the line y equals x? Nope. Okay. And how about the line, this one? Y equals x plus 1. All right. So let's take a look at this one. So if I were to kind of like put a nail in the origin, right? And if I spun this whole picture 108 degrees around, right? If I basically take your notebook and turn it upside down, you would see that this function lands on itself, right? So this is odd. Same thing here. Put a nail here and spin your notebook 180 degrees around. This function lands on itself. This is odd. Now this one is very interesting. If I put my nail here, right, and I spin my 100, or you take your notebook and turn it upside down, you will notice the graph does not land on itself. It lands down here. This function is not odd. Okay, I want to be very clear about that. This function does have rotational symmetry about this point right here, but that point is not the origin. Okay, so this function here, notice something. This function is not rotationally symmetric about the origin. It's also not reflection symmetric about the y-axis. So this function here is neither even nor odd. There's nothing special about that function. And of course it's wrong. There's plenty of things special about everyone, but just not in the context of even or odd, okay? So we would say this is neither even nor odd, all right? Okay, algebraically, if f of x is odd, then here's the property. If f of x is odd, that means that negative f of x will equal f of negative x. Okay, you may see it in textbooks. It says this: f of x equals negative f of negative x. These two things are saying the exact same thing, right? If I just divide by -1, I get this. All right, but let's take a look at what this is saying. This is saying, if I negate f of positive x, right? So here is f of x. Negative f of x would be boink down here. That y value is the same thing as the y value at negative x. So here's negative x, boink, there's the y value. So I can kind of visualize that, what this is saying, right? Okay. Or this one's saying is the y value of the function will equal the opposite of the y value when you input the opposite x value. Okay, so let's work with f of x equals x cubed. Let's do the similar example from above. So if f of x equals x cubed, let's show that one of these is true. Oop. Okay, well, let's see. Okay, so negative f of x would equal negative x cubed. Be careful of order operations here. As it's saying x is cubed, then you're negating it. Okay, let's see. F of negative x would equal, negative x cubed. But negative x cubed means negative x times negative x times negative x. A negative times a negative times a negative will equal a negative x cubed. And you see how these are the same? So function is odd. So question for you. Is there a trigonometric function that we have seen, a periodic function that is rotationally symmetric about the origin? Yes, there is. Take a look at y equals sine x. I'm just going to do a really quick sketch here. What color shall I use? I think I like this little olive. Okay, y equals sine x looks like this. That is unless, of course, you're pheno, in which case it probably looks something like, I actually don't have words to describe your graphs, pheno. They are that challenged. Notice I didn't say bad, I said challenged. That's okay, we can always, laughter has to be a part of our everyday work. This is the graph of y equals sine x. Oop, I just put a nail there, my little rotational nail. This is f of x equals sine x. Do you agree that if I were to turn my paper upside down or rotate this graph about the origin, it would land on itself? Yes, it does. Okay, well, let's do this. Let's see, is it true that negative f of x will equal f of negative x? Okay, let's see. Negative f of x would equal just negative sine x. But f of negative x would equal sine of negative x. Oh no, let's think. Let me think about my quadrant. Sine is positive in quadrant 1. Sine is positive in quadrant 2. Sine is negative in quadrant 3. Sine is negative in quadrant 4. So, and some of you may see this very quickly, and those of you who don't worry, I'm going to think out loud with you. So the question is, what can I say about like the sine of negative 45 degrees and the sine of, I don't know, negative 120 degrees and the sine of, like negative 300 degrees? How do they relate to the sine of, like, what's the relationship between, in fact, let me erase this. What's the relationship, because we don't know if it's equals, right? Let's just put like a blank box. What's the relationship between, sine of negative angle versus the sine of 45 degrees? Well, let's see. First of all, if I'm comparing, let's start at the bottom. If I'm comparing negative 300 degrees and positive 300 degrees, I think we both agree, well, not both, all 16 of us would agree that both these angles have the same reference angle, right? But let's think about what quadrant they terminate in. Negative 300 degrees would terminate in quadrant 1, where sine would be positive. I'm just going to make a little note to myself. Sine would be positive. Sine of 300 degrees, oh gosh, that's the wrong place for it. So this would be a positive number, but sine of 300 degrees would terminate in quadrant 4, where it would be a negative number, right? And sine of negative 120 would terminate in quadrant 3, where sine would be negative, and sine of positive 120 terminates in quadrant 2, where sine is positive. And sine negative 45 would be negative, but sine 45 would be positive. Oh, I see a connection. I think it's pretty obvious that the sine of a negative angle will equal, I can't say it equals sine of the positive angle, it equals the opposite of, that should be a negative sign. Should be a negative sign. I'm trying to emphasize my negative sign. So sine of a negative angle just equals the opposite of the sine of the positive angle, which then brings me back to this puzzle here. If f of negative x equals sine negative x, I know that sine negative x is just negative sine x. And I have shown that f of negative x and negative f of x are the same. So I have algebraically shown that y equals sine x is an odd function. Okay, that concludes this screencast. Goodbye.